In the last few lectures, we considered liquid based solar collectors. In general, they are water heaters, though occasionally antifreeze of fluid also is used. It may be used for heating other liquids also. Apart from that, solar collectors in the category of flat plate collectors are also in wide use based upon air as the fluid. In general, most of the time no other gas is used to heat through a solar collector. The importance of air based collectors comes into the picture because of a large number of applications for hot air. It could be space heating in colder climates, various drying applications, and solar in that sense is ideally suited, because if you want space heating, it requires temperature slightly greater than or equal to 20 degrees C to be maintained for comfort condition under cold climatic conditions. Drying applications typically will be 50 to 70 degrees C, and normally not at a very high temperature. Some of the things are, it could be tablets, medicine tablets in the pharmaceutical industry, or it could be cash crops like cardamom, tea, coffee, etc. We will talk about these things in detail little later part of our lecture series. The important point is the temperature should not exceed or is not used, because along with that the flavor and the oils also get evaporated, which we do not want in any food product. So, air based solar collectors derive their own strength for good number of applications, and solar flat plate collector with a reasonable efficiency at about 50 to 70 degrees centigrade is operable. Consequently, this appears to be a promising application or promising device for different applications. However, one deterrent appears to be larger pressure drop through solar air collectors compared to all liquid heaters. That we shall again consider, and I am showing here a typical air heater. You have a duct, the top one is the absorber, the fluid flows entering at a temperature of DFI and leaving at a temperature of TFO. The bottom is insulated and top will have one or two glass covers. So, this will be having a emissivity of epsilon p and absorptivity of alpha p. Similarly, the bottom plate may be having an emissivity of epsilon b, though absorptivity does not come into the picture, and this part is insulated. So, as the heat is absorbed, this is the direction of flow, and as the heat is absorbed, transmitted through the glass cover by the top cover, it is transferred to the fluid with a heat transfer coefficient of H of 1 and again another heat transfer coefficient to the bottom with H of 2. This is typically at a temperature of T P m as we have been doing, and the bottom is at T B m. That means, we follow a single node approach. The absorber is represented by one temperature, the bottom plate is represented by another temperature, and there is of course a heat loss coefficient from the top U T, and a bottom heat loss coefficient of U b. So, we shall try to analyze, and I shall show a small control element. The at any particular distance x and an elemental length of delta x, the fluid enters at a temperature of T f and leaves at a temperature of T f plus delta x, and the total length could be L 1 as we have seen, length of the duct and let also width W, which is perpendicular to the plane of the paper. This analysis is due to Wheeler. Reference also is given. This is similar to the analysis we followed for the liquid collectors, and we need to calculate transmittance absorptance product for the direct radiation and the transmittance absorptance product for the sky diffuse radiation and the transfer absorptance product for the ground reflected radiation, along with the top loss coefficient U t and the bottom loss coefficient U b. In other words, this is calculated at theta b, and this is calculated at theta d, and this is calculated at theta g, the correlations of which have been given by Brandmühl and Beckmann, and this is the angle of incidence for the direct radiation at the given time under consideration. Let the flow rate m dot and the plate is at T P m and the bottom is at T B m, which we have already identified as a single node approach. Now, we will make an energy balance for the absorber, then the bottom plate, and the fluid. Here is our notation. S is the absorbed solar radiation, which we know is I t times tau alpha, where I t is the solar radiation on the tilted plane, and your tau alpha is the combination of tau alpha b, tau alpha d, and tau alpha g. And U t, of course, we have stated as the top loss coefficient, and U b the bottom loss coefficient. Then H 1 is the convective heat transfer coefficient, from the absorber to the fluid. Similarly, H 2 from the fluid bottom plate to the fluid or from the fluid to the bottom plate. The heat transfer direction will depend upon the relative temperatures. Epsilon P is the emissivity of the absorber, and epsilon B is that of the bottom plate. So, if you want to have another view of this air heater, you have a sort of rectangular duct. This is the width W that is not seen, and this is the length L we are talking about, and the flow is now through this rectangular passage. This entire thing is having a glass cover at the top and a bottom insulation. So, the energy balance on the absorber plate if S is the absorbed energy, area will be W into dx, that should be equal to U top into W dx times T P m minus T A, this is a loss, plus H 1 W dx T P m minus T f plus sigma W dx by 1 upon epsilon P plus 1 upon epsilon B minus 1 times T P m to the power 4 minus T B m to the power 4. Let me explain. The absorbed energy is S per unit area, and in the elemental area we have considered area as W into dx. Of this absorbed energy, something is lost to the ambient through the loss coefficient top U t, and something is transferred to the fluid with the heat transfer coefficient of H 1 and the temperature difference being T P m minus T f, and then also from T P m to T B m there is a radiative heat transfer parallelly taking place, whose value is given by sigma into the temperature difference 4 power into area by the normalized emissivity, which is epsilon P plus 1 upon epsilon B minus 1. Now, for the bottom plate, what it receives is sigma W dx by radiation from the top plate this should be equal to H 2 times W into T B m minus T f plus U B into T B m minus T A times W dx, there should be a dx here also. So, this is what it receives by radiation, and this is what it transfers to the fluid, assuming T B m is more than T f, and this is the again loss from the bottom with the bottom loss coefficient of U b and to the ambient temperature T A. The energy balance on the fluid m dot C p into temperature raised should be equal to what it receives H 1 W dx into T P m minus T f plus H 2 into W dx times T B m minus T f. As long as we are consistently writing this, the sign of T B m minus T f will take care of whether it is an addition or a subtraction in making dTf for the airflow of mass flow rate m dot. So, we can define a radiative heat transfer coefficient like we have done earlier based upon Tpm minus Ta, which is equal to sigma 1 upon epsilon p plus 1 upon epsilon b minus 1 times Tpm to the power 4 minus Tbm to the power 4. This is nothing but expressing the radiative transfer in terms of a heat transfer coefficient Hr, and we solve, and Hr will be equal to, again will be written as Tpm squared minus Tbm squared into Tpm minus Tbm, or an approximation can be made if Tpm minus Tbm is small, so this fourth degree difference can be written as 4 times T average cube times Tpm minus Tbm, where this T average is Tpm plus Tbm, arithmetic mean of the two temperatures. So, Hr now is approximately 4 sigma T average to the power 3 by 1 upon epsilon p plus epsilon b minus 1. So, now we have written the energy balance equations on the absorber, the bottom plate and the fluid, and the radiative heat transfer coefficient has been expressed in terms of an average temperature little approximately compared to the exact equation. Another simplification, though it is not that we cannot do the analysis, we can do this. UB is assumed to be much smaller than top loss coefficient. What we are saying is, if the bottom plate temperature is low, the losses from the bottom are much smaller than the radiative and convective losses from the top glass. So, with this simplification, I will call them some numbers. A equation, this absorbed energy from the first equation follows UL into Tpm minus Ta plus H1 into Tpm minus Tf plus Hr times Tpm minus Tbm. Wdx in the equation first we have written is common throughout. So, that is cancelled and you have the absorbed energy equal to whatever is the loss plus whatever is the gain by the fluid and whatever is transferred to the bottom plate, and Hr Tpm minus Tbm simply equal to H2 times Tbm minus Tf. Whatever is transferred by radiation should be convected to the fluid. On the fluid, this is a equation we will call it B, and then m dot Cp by W dTf upon dx equal to H1 times Tpm minus Tf plus H2 into Tbm minus Tf. The rate of increase of the fluid temperature in the x direction is equal to whatever it is gaining from the absorber plate plus whatever it is gaining from the bottom plate. And from this, T B mean is Hr Tpm plus H2 Tf upon Hr plus H2. So, substitute in A plate mean temperature will be S plus UL times TA plus HE into Tf by UL plus HE, where HE is a equivalent heat transfer coefficient. So, this is nothing but a simplification in the notation. In other words, instead of a long expression H 1 plus H r H 2 upon H r plus H 2, we simply write it as H e. So, it can be called an effective heat transfer coefficient between the absorber plate and the air stream, because it comprises of convection from the absorber plate and again convection from the bottom plate. So, from this you can now express T P m minus T A equal to S plus H e into T f minus T a by U L plus H e. So, from C equation m dot C p by W d T f by d x equal to S minus U L times T p m minus T a. You may realize that this analysis is exactly similar to what we have done for the liquid based collectors, but since there is no fin effect involved in the absorber, that is a simple equation, and the rate of change of in the direction of the flow we are having exactly similar to what we had for the liquid heaters. So, this can be rewritten m dot C p by W into d T f by d x is 1 upon 1 plus U L upon H e times S minus U L into T f minus T a. So, this is in terms of the mean plate temperature and this is in terms of the mean fluid temperature. Consequently, if you recall, this is f dash now is given by 1 plus U L upon H e to the power minus 1, because how did we first define? Useful energy gain Q u is A c times S minus U L into T p m minus T a, which is the same as A c into collector efficiency factor f dashed times S minus U L into T f m minus T a. So, the other two equations, one is in terms of T p m and the other is in terms of T f, and with a multiplication factor of 1 plus U L by H e to the power minus 1, which hence will be equated or called the collector efficiency factor. So, now the equation for the fluid m dot C p by W d T f by d x will become equal to f dashed times S minus UL into TF minus TA. So, one can integrate this is a first order equation. S by UL plus TA minus TF by S by UL plus TA minus TFI should be equal to exponential W F dashed UL into X by M dot Cp. So, we used the condition at x is equal to 0, Tf is equal to Tfi. So, if I express the useful energy gain in the conventional manner, Fr into Ac times S minus UL times Tfi minus Ta. Now, Fr is your heat removal factor. So, exactly similar to what we had done for liquid collectors. M dot Cp by Ac UL times 1 minus exponential F dashed UL Ac by M dot Cp. This is with a negative sign. Okay. So, Ac is the area W into L. If so, now this is exactly whatever we had in the case of liquid collectors. One can also again define a flow factor F double prime equal to Fr by F dashed equal to M dot Cp by Ac UL F dashed times 1 minus exponential minus F dashed UL Ac by M dot Cp. As we had noted earlier, the expression for F dashed may be different or F may be different, but this flow factor expression is in terms of one non-dimensional number, which is M dot Cp by Ac UL F dashed. We call it the non-dimensional flow rate. For lack of a better word, we will call it the non-dimensional flow rate. If the simplification UB is far less than UT is not made, the differential equation would be, you can work out, it is straightforward, M dot Cp by W dTf upon dx equal to F dashed times S minus some UL double prime times Tf minus Ta. So, this UL double prime is equivalent loss coefficient. So, now f dashed and u l double prime are given by as usual sorry to the power minus 1 and this u l double prime will be u l dashed plus 1 upon f dashed u b h 2 by h r plus h 2 plus u b. So, this overall effective loss coefficient will be a function of the collector efficiency factor also. And again u l dashed, you may be surprised that this is a new thing, is nothing but our original u t plus h r u b upon h r plus h 2 plus u b. So, you will have that u l dashed will be u t plus this one, if f dashed is equal to 1, u l dashed will be equal to u l double prime, and of course, h e is h 1 plus h r h 2 by h r h 2 plus u b. Now, you may be wondering, too many equations are being written. So, what I would suggest is you go back and starting with the 3 equations that we have set up with the simplification that u b is far less than u double prime or u l and sorry top loss coefficient u t, and then simplification followed. You do not make that assumption, then rederive exactly along the lines that we have done, these equivalents will follow. So, q u f r a c s minus u l double prime by t f I minus t a, and again of course, this f r will be in terms of m dot c p u l double prime a c times 1 minus exponential to the power minus f dashed u l double prime a c by m dot c p. Now, question: why u l double prime here instead of u l equal to u t plus u b? You will notice u double prime is u l dash plus something, and where u l dash is u t plus something, right. In the case of liquid heaters, that your u l is nothing but u t plus u b, and here there is no direct heat transfer loss from the working fluid, okay, or is there? Now, some time back we pointed out u l may not be equal to u t plus u b if the working fluid is in direct contact with a heat losing surface. Here what is happening is the heat is being transferred to the fluid from the top absorber plate by convection, and by radiation it is transferred to the bottom plate, and in turn the bottom plate also is transferring heat to the fluid or losing heat from the fluid. Consequently, you may consider that this is a case of fluid coming in contact with the surface losing heat. So, we shall continue with the theory of air based solar flat plate collectors. One of the concerns what we said was the pressure drop and heat transfer. In air ducts. All right. First, the convective heat transfer coefficient between absorber and the fluid, that is our H1, and this is a case of a duct subjected to some flux, some q dashed, and bottom being insulated. Some of you who are familiar with little bit of advanced convective heat transfer, there are basic four types of boundary conditions. One is insulated, the other is constant temperature, or the insulated and constant heat flux, so on and so forth. So, this is one of those basic boundary conditions. Now, there is what is called a fully developed condition. This we can call it for fully developed flow or temperature field or both. So, if you consider the classical thing that you may be aware of, a pipe flow and let us say laminar flow, the standard velocity profile is parabolic, fully developed. So, this condition generally we state it as du dx, if this is the direction of x, equal to 0. So, there is no more change in the velocity in the axial direction with respect to x. It still is a function of radius, but not that of x. But again in the beginning, the both u will be changing with respect to x, consequently the normal component of velocity also is not equal to 0. And the corresponding thermal field is said to be fully developed if T minus T w by T b minus T w is invariant with x, okay, or d by dx of T minus T w by T b minus T w equal to 0. In other words, there exists a non-dimensional temperature defined by T, as a matter of fact it is a function of x and r, and T b a function of x only, because it is the integrated average temperature at a section that does not change with respect to x under fully developed temperature field. This is satisfied by constant temperature and constant heat flux boundary conditions. Of course, we shall not go deep whether the flow is developed or thermal field is developed, which one develops faster, that is not in the part of this particular course. And generally it is considered for ducts fully developed if length by some d e is greater than about 30. So, if we take an example, small example, let the length duct be 1.5 meters and let the channel be, rather flow area be equal to 1 centimeter by 1 meter, right. This is, in other words, is something like this. This is 1 cm, this is 1 meter, and this is 1.5 meters. These are quite typical airflow or collector dimensions, one can consider to be so. We define that d e is the equivalent diameter or also called hydraulic diameter and so this d naught will be, I will write down the formula a bit later, 4 times 0.01 into 1 divided by by 2 equal to 0.02 meters. So, this is I think the length is L is taken as 2 meters, that is okay. So, just for using the calculation. So, this L upon d naught will be how much it will be? 4 times flow area by, okay, this is okay, this is all right, 1.5 does not matter. L by d naught will be 1 by 0.02 equal to 50. Okay. Just one second. Okay. L is 1 meter, is also 1 meter. So, finally, L is equal to 1 meter, W is equal to 1 meter, and that thickness is 1 centimeter. This hydraulic diameter is 4 times the flow area by wetted perimeter. That is why we have written 4 into flow area is 0.01 meters, that is 1 centimeter, multiplied by W is 1 meter, by wetted perimeter is, this is 1 meter, 1 meter, 1 centimeter. If we neglect this 1 centimeter, it is 1 meter plus 1 meter, which is 2. Okay. So, that is we got it as 0.02 meters, and now L by d naught is 1 upon 0.02, which is equal to 50, which is greater than 30. So, a 1 meter by 1 meter duct with 1 centimeter passage width can be considered as fully developed conditions. What we have here is the correlations for the Nusselt number. First of all, the flow is turbulent, fully developed, and Nu is 0.0158 Re to the power 0.8. This is a result due to case. Now, I have to define Nu. Some of you who are not very familiar with heat transfer is the Nusselt number equal to heat transfer coefficient times this d equivalent by thermal conductivity of the fluid K. Then Re also U average times dE by kinematic viscosity. Okay. So, K is the thermal conductivity, of air or fluid, and kinematic viscosity. This has got the units of meter square per second, and this has watts per meter degree centigrade. Okay. Another correlation is due to Malik and Bulow, which is again given in your reference in the notes 37. Again, Nusselt number is related to 0.0345 4 RE to the power 0.75 by 1 minus 1.586 RE to the power minus 0.125. So, as we have already explained, a D naught or DE, D naught or DE, the hydraulic diameter, is four times flow area, or sometimes it is also written by, just one second, wetted perimeter. Or 4 times cross sectional area of the duct by wetted perimeter. Though one easily understands that these two are equivalent, at times it could be bit confusing when you talk about cross sectional area of the duct in the strictly drawing terminology. It may be the area of the pipe material when it is cut across. So, it is desirable that we use the word flow area, that means it is the area through which the flow is taking place. And most of the time H 1 and H 2 are taken as equal. This is certainly needs investigation, subject to some questioning. However, in the solar, in view of other uncertainties and the flow is turbulent or laminar, that H 1 and H 2 are taken as equal. So, we know for air collectors the governing equations have been obtained by making an energy balance on the absorber plate and a bottom plate and the fluid, with a certain simplifying assumption that U b is much smaller than the top loss coefficient. We obtained relatively simpler expression, and this can be recast exactly in the form that we do for the liquid collectors, A c into F r times S minus U L into T F m, sorry, T F I minus T A. Though your definition of U L in terms of U b and U t will be different, and the heat transfer coefficient equivalent has to be defined in terms of H 1, H 2 and H r. Okay? The radiative transfer coefficient between the top plate and the bottom plate, and the convective heat transfer coefficients from the top plate and the bottom plate, and top loss coefficient U t and the bottom loss coefficient U b. S is of course the conventional absorbed energy given by I t times tau alpha. Okay? That is it. Thank you.